Again, this does have two different approaches. Like the last one, I will show you a classical. I may ask one homework question that asks you to do classical, but ultimately on tested quizzes, I will only ask for the classical. So, just like with the other one, I'll show you the classical, but that's not what I'm going to be assessing. The requirements, just like when we were dealing with the mean. We have to have a sample obtained by simple random sampling, has no outliers, and the population is normally distributed, or the sample size is large, and the values are independent. Basically, what you need to check at the beginning, we always have to check criteria. With the binomial, with the p's, we had that it had to be simple random and they were all independent, and I made you check if it was normal. The n times p times 1 minus p greater than or equal to 10. The thing that I will be looking for on every problem, are you checking to see if, does it either say in the problem that it's normal, or is your sample size more than 30? Okay, that is the piece that you need to check every time. Then we will do our null and alternative hypothesis, just like with the p's, except for a mean, we'll be talking about a mu. We'll have to have our alpha, just like before. That's our probability of making a type 1 error. Here's what's different. Remember when we did the confidence intervals for the x-bars, we used t's? They're coming back. So we will compute our test statistic, our t. This is all, if you guys look on your formula sheet, chapter 10, it has your formulas for your test statistics. It has the z formula, and it's got our t formula. Essentially, this is just like calculating a z. It's your observed value minus your mean over this thing represents your standard deviation. When we talked about, if you look at chapter 8, it told you your mean was mu and your standard deviation was your s over radical n. So we've used those before. So we'll calculate a t value, which means we will be using not the normal table, but the t distribution when we're looking at these. Then we will, if we're doing the classical approach, we will have to find a critical value and compare that with our test statistic. So I'm trying to remember on the homework, I think I may have given one or two that asked you to do this. This is the part, it takes a lot more thought than a p-value approach, so we'll talk through one, but ultimately we'll go the other route. But basically you'll find the t-value and you're going to compare that with your t-alphas. With the p-value approach, you're still computing your t, but then we are going to have to look at it in terms of areas, the probabilities. So we'll be reading probabilities from there. Okay, example 1. I gave you like 2 length slides after example 1 because I'm going to show you how to do example 1 all the ways we have to do it. Okay, and then moving forward, we will just do it one way. Assume the resting metabolic rate of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found the mean to be 5,708.07 with a standard deviation of 992.05. At the alpha equals 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than the 5,710? Okay, so very wordy, but let's go through and pick out our information. It's going to start out really the same way as the last one. The very first thing you have to do is check the criteria. Now that we have both p and mean, you're going to have to pay attention in your problems. But if you look in your problem, it tells you we're talking about the mean RMR. So when you get to a test or quiz, you'll just look, is it a proportion or is it a mean? So if it's talking about the mean, the criteria you need to check is, did it tell us this was normal? No. So then we need to see, is our N bigger than 30? Yeah. 45 is greater than 30, so that means we can assume it's normal. So check your criteria first. Then we get into our hypothesis. Our null and alternative. The null hypothesis, since I'm talking about a mean, it has to be mu, equals what? What did they think it was at the beginning? What are we comparing it to? What's our baseline?
5708107.
That's what they observed in their study. Yeah, this is what we are assuming to be true, 5710. Our alternative, I want to know, is it different? So that would be not equal. Okay, so just like last night's, check your criteria, do your hypothesis. Now, we are going to have to compute our t statistics. So we need a few things. What is my x bar in this problem? The sample mean.
5,708.07.
Okay. What is my S, my sample standard deviation?
992.05.
So now we're going to find our t. T is your sample mean minus your true mean, which was the 5710, divided by the standard deviation. The formula that your book gives has you do it all at once. Usually we kind of calculated that out to the side, so if you would prefer to calculate it before, you can. The standard deviation we're going to use is S over the square root of n. So if I do that, that is going to be, I'll call it my sigma, my standard deviation. So I get 147.8861, so that's what we divide by. It's always your observation minus the mean over the standard deviation. Okay, this will give us our t value. So I get negative 0.013. That's the same no matter which approach you're taking. That's your starting point. Now let's talk about the different ways of doing it. If you go with the classical approach, which, I'll say it again, I may put 1 or 2 on the homework, but I will not do classical on test or quiz. Okay? With the classical approach, we need to find, since it is a not equal, that means it could be 2 tails, so we have to do the t alpha over 2. If it's just a 1 tails, you do t alpha. But 2 tails, we have to split it up. So my t alpha over 2, what was alpha? So I get t 0.025. Now remember, on the t, you have to know your degrees of freedom to look it up. How many degrees of freedom do we have? 44. It's n minus 1. So here's the problem. Go to your T table. Okay, do we have a .025 column? Yes. Do I have 44 degrees of freedom? No. We have to go with the closest we can, which would be 40. Now, that means our answer is not going to be exact, but it's in the ballpark. So if you match those up, we get, okay. Now, because it is two-tailed, the T distribution gives you the area to the right. Basically, you found that if your T is .021, the area right here is .025. But we divided our alpha in two because we had a two-tailed test. This one down here has to also be .025 because of that not equal, because it's a two-tailed test. So what would this T value be down here? Okay, so here's the downfall of the classical approach. You can't just read the T from the table and be done. You have to think about, am I talking about the positive, the negative, or in this scenario, both, because I have two tails. So we need both the positive and the negative here. Okay. Then the classical approach says compare this T to the T we calculated before. Okay, the center is like when T is 0. We will reject if our T is in either of those places. So bigger than 2.021 or smaller than negative. So if it's in this shaded region, we reject. If it's in the middle, we don't reject. My T is negative .013. So what will I do? I will keep it. It's in the white region. That's the acceptable window. So we will fail to reject here. So with the classical approach, you're going to have to look at it. If my null hypothesis had been T is, or the mean is greater than, you would not have divided by 2 because it would be a one side. You would get your T value, and the T distribution does tell you the greater than. So that would be what you use. If it asked for less than, you would do the negative of whatever you found. And since it was two-tailed, we had to do both positive and negative. Okay, so there is that, with the classical, there is that piece that you actually have to interpret. You can't just read the T value and be done. You have to think, is it positive, negative, or both here? Now, let's talk about the P value. The P value says we are going to actually find the probability of this occurring. So we have already found, what did I get my T to be on the last slide? The negative .013, was that it? Mm-hmm. Okay. So just like when we were doing our P's, our P value approach, we'd find the probability that Z was greater than or less than that value. Because I have a two-tailed approach. Okay, so here's my T. I can find this, but it's two-tailed, so I really need this one as well. Now, we have to decide which one we actually want to look up in the table. When it was normal, we always looked up the one on the left, because the normal table gives you the area to the left. But the P table, if you look at it, it's telling you the area to the right. So what I'm going to find is the probability that T is greater than. And then since I have two of those, they're symmetric, I just need to take that times 2. Okay? And again, that's because it's a two-tailed test. Now, again, we have a downside. We are looking for the T. So this is, we're looking for our probability. This is the number inside the table. So we need, how do I want to phrase this? The area closest to 0.013 in the table with 44 degrees of freedom. Now, huge downside of that. Looking at your table, I have a 40 degrees of freedom row. I don't have 44, so already I'm limited. Now you are just looking at that row. If I'm looking at 0.013, what's the closest I can get? 0.681 is the closest this table even shows me. Did you guys all see that? It's not very close. Now if I was looking for like a 0.7, it wouldn't be as far off. But I'm looking for 0.013. So we are pretty limited here. We are going to ballpark it as close as we can. So the closest we can do is that 0.681. So go up to the top. What is that area? Times 2, and we get 0.5. Now, we know that's horribly wrong, but it's the best this table would do. Just like before with the p-value, now you're just going to compare that to your alpha. If it's smaller than alpha, you reject. If it's bigger than alpha, you fail to reject. Since 0.5 is bigger than the alpha of 0.05, we fail to reject our null. Okay. So I've shown you classical, I've shown you p-value. But can we all agree that we are very limited by this table? It is not all-inclusive. So the third way I want to show you is on your calculator. And it will be the most exact because this t distribution is not the best. Okay. Everybody have a calculator? You are going to go to Stat, Tests. Okay, the last one we were talking about the p-value, so we did a one proportion z-test. What do you think we're looking for this time? T-test, number 2, the t-test. Okay. On this, you have to select how we want to do this. There is input, data, and stats. Sometimes I might just give you a table of values and we'll enter it in our L1 and ask it to calculate it from that table. This one, I don't have the raw data, so I'm going to select stats. Okay, then it asks for your mu sub 0. That is what our null hypothesis is. So that's our 5,710. So I did stats. Okay, your x bar was your observed mean, which is the 5708.07. Your S sub x standard deviation was 992.05.
How do you know whether to do the standard deviation or like the standard deviation over?
Your calculator will go ahead and calculate the new one for you. So it's just asking for the standard deviation of x itself, not for x bar. Your n, how many people were we looking at here? Okay, the test we were doing, and we don't want a picture, we want to calculate. Okay, and it tells me my t is negative 0.013, which we got, but our p is 0.9896. What do you notice about that? Is that close to what we found when we did it by hand? No. I mean, it's going to lead us to the same conclusion. We reject because this is most definitely not smaller than 5%. But it is much, much larger because our table, we had to use 0.68 to get close to 0.013. We were really off. So most of these, I am going to just use the calculator because it is way more exact than the table that we have.
But no matter what way you do it, you should end up.
You should get the same conclusion, yes.
It may just not be as.
Yeah, your p will be a little, yeah. But as long as I know how you're getting there, you should get the same conclusion. All right. Let's do another one. I'm going to do it both. I'll do it by hand and on the calculator, but just with the p values this time, not the whole thing. Okay. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from the 5.67 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. At the alpha equals 0.05 level of significance, is there evidence to conclude that the state quarters have a weight different than 5.67 grams? Okay. So my conditions, I left out. I meant to tell you that this was normal. I left out that sentence. We don't have 30 or more, do we? No. I meant to say it is normally distributed with a weight. Because without that, if I didn't tell you, you wouldn't be able to do this. Okay, so this is normally distributed. I'm telling you.
I'm going to do it without it being normal, just like the other ones.
Yeah.
You're just popular today.
I'll record this. Okay, so let's do this on the calculator first, and then we're going to do it by hand. Show it, okay? So if you want to do this on the calculator, you're going to go to Stat, Tests. We are doing a t-test because we're talking about the mean. Your input is data this time. Your mu is, what was the mu in the problem? 5.67. Oh, we should write our hypothesis before we do this. What's my null hypothesis? Be the mu equals 5.67. The alternative, what am I trying to decide? If it's different. So then on your calculator, your mu is 5.67. Your list, make sure that says L1. If it does not, I can change it for you.
And what's the frequency supposed to be?
Frequency should be 1. Choose the not equal to, calculate. So on our calculator, it tells us that our T is 2.753, P is 0.0136. So would we reject the null? Yes, our P is smaller than 0.05. So we would reject.
Wait, we're only worried about P right now, or T?
The T is
Okay.
just kind of, I write it down to check, but the P is the thing you're looking at. Okay. So in this one, we would reject. Now, if I asked you to do this by hand, let's walk through the by hand one more time. We have our hypothesis. We need to calculate our T. So to do that, we have to have the X bar and our mean and standard deviation. So the X bar given in the problem, do we know that? It didn't tell us, did it? It gave us data. We entered that in our calculator. Go to Stat, Calculate, One Variable Statistics. And then you should be able to,
X bar 5.702.
yeah, remember when we did this before? We are also going to need the S from here. The S of X in this is 0.04965. Did everybody get that? So if I give you the raw data, regardless, you're going to put it in your calculator at least to get the mean and standard deviation. So now, for calculating, we will use the 5.67 for our mu. The standard deviation, we do this standard deviation divided by the square root of n, which was 18. Which gives us a 0.0117026. So our t is your x value, your x bar, minus the mu. If I do that, I get my t to be 2.75. So now, since we're doing this with the p-value approach, you have to think about this one was a not equal to again. So talking about 2.75, we're looking for these probabilities, but we would also have to do a negative 2.75. The easiest way to do that is just 2 times the probability that it is greater.
So we have to do that every time, even if it's not 2-tail?
No, this one is 2-tail.
It's not equal?
If it wasn't 2-tail, you would not have to multiply by 2. Okay, so now we are going to read this from the calculator. How many degrees of freedom do we have? 17. Okay, so everybody go to your t-table. Let's make sure we can read this. So we know this is not the best way, and we're probably going to do all of these on the calculator because it's not that accurate. We do have a row for 17. I am looking for the closest I can get to 2.75 on that row. So 2.75 falls, yeah, it falls in between the what? 2. Okay, everybody find that? So now we need really just which one's closest, which would be I think if you subtract them, the 2.898 is actually a little closer. If you go to that then, reading up at the top, what's the probability there?
0.005.
If you take that times 2, you get 0.01. Is that less than 0.5? Or sorry, less than 0.05? So we still reject. Okay, so this method's not great because we're estimating. The calculator is better for this one because it is much, much more accurate. Did I print the assignment on those?
Yeah.
Okay. We are going to finish this section on Monday. We'll do one more example, but really you know how to do it. So you have on Monday, I am grading the 10.2 homework. We'll do the last example, and then you will have some time to work on these book problems. You are welcome to start them before.